This is the second lecture on incoherent scatter radar measurement techniques. In this lecture, I will cover radar signal processing techniques. In addition to the usual amplitude domain radar signal processing methods, I will cover power domain techniques, which are needed in order to estimate the autocorrelation function of the scattered signal as a function of range. These techniques are required when measuring ionospheric plasma parameters using incoherent scatter radar, due to the Range-Doppler overspread nature of ionospheric radar echoes. Here is an overview of the topics that I will cover in this lecture. I will first introduce the range time diagram. Range time diagrams can be used to model how a radar transmit waveform signal and the signal received by a radar receiver are related to the range time distribution of radar scatter. Using a range time diagram, I will first discuss how radar pulse length and receiver filter length are related with range extent, or in other words, the range resolution of a radar measurement. I will use a Fourier transform to derive a relationship between the transmit signal bandwidth and range resolution. After this, I will introduce a discretized range time diagram, which we will use throughout the rest of this lecture to model radar signals and to derive signal processing techniques. Radar scattering can be roughly categorized in two classes: coherent and incoherent radar targets. For these two types of radar targets, we will need to use different types of signal processing techniques. I will describe what this means in practice. I will first introduce methods for analyzing coherent radar targets. In this case, the measurement can be modeled as a convolution, and the signal processing techniques are equivalent to techniques for deconvolution. I will discuss the matrix linear least squares, inverse filtering, and match filtering techniques that can be used for deconvolving the radar transmit signal from a measurement to obtain an estimate of scattered complex voltage as a function of range. I will then discuss techniques for incoherent targets. I will first introduce the Range-Doppler dilemma and tell you why techniques applicable for coherent targets cannot be used for typical incoherent scatter radar measurements. I will cover three commonly used techniques that can be used to measure the autocorrelation function of radar scatter as a function of range: the double pulse, the multipulse, and the coded long pulse. In the previous lecture on measurement techniques, I told you that we obtain radar echoes from a localized volume in space. I also stated that the volume is defined by the solid opening angle of the radar antenna, as well as the range extent of the volume, which depends on the length of the radar pulse, T sub p. In this lecture, I will show how we can relate complex voltage measured by a radar receiver to the range extent of the scattering volume, which is defined by the range to the volume R and the range extent of a radar pulse, delta R. In order to do this, we will first introduce the so-called range time diagram, which can be used to visualize how the range extent of a transmitted radar signal depends on time. This is a range time diagram. The concept is simple. The x-axis denotes time, and the y-axis denotes range. When we send a radar pulse, the pulse travels in range with the group velocity of the electromagnetic wave. In most cases, the group velocity is nearly identical to the speed of light in vacuum. However, in some precision measurement applications, such as observations of satellite trajectories, the group velocity of the electromagnetic wave in magnetized plasma needs to be taken into account. We'll now extend our range time diagram to include the propagation of a radar pulse from the transmitter to a scattering volume at range delta R. We will assume that the radio transmitter is in the same location as the receiver. The concept of a range time diagram can be extended for bistatic radars, but we'll try to keep things simple. After propagating to a radar target at range delta R, the radar signal is scattered and it then makes its way back to the receiver. I've denoted the up and down leg of the radio wave with lines with slopes of c and minus c. The time difference between the transmission and reception is denoted with delta t. Taking into account the round-trip propagation of the electromagnetic wave, we can relate the range delta r to the propagation delay delta t as follows. The factor of 2 arises from the round-trip propagation of the electromagnetic wave. If we now extend our range time diagram to include a transmitted radar pulse of length t sub p and a receiver filter length equal to the transmit pulse length, we get the following diagram. In this case, there is a difference between the leading and trailing edge of the transmitted pulse, as well as the leading and trailing edge of the received signal sample. If we use a receiver which integrates the received complex voltage for the duration of the transmit pulse, the integrated signal will be a sum of the scattered signal within the gray box shown in range time space. A radar receiver therefore receives a sum of radar scattering over a closed area in range time space. The mean range of a radar echo after a propagation delay of delta t is the speed of light times delta t over 2. However, echoes from ranges between plus minus the speed of light times the pulse length over 2 are also received. I have sketched the distribution of received power as a function of range in the subdiagram on the right. The full range extent is the speed of light times the pulse length. However, most of the received power comes from half of this range extent, and this is what is commonly used as the range resolution for this type of a measurement. The time extent of the received signal in range time space is similar. I have sketched the distribution of scattered power as a function of time above. The received power is centered at delta t over 2, and the full extent is the transmit pulse length, t sub p. If we now extend our diagram to include 2 receiver samples and 2 ranges, we can see how the scattered signal is distributed in range time. The mean range for the scattering volume n+1 is shifted by the speed of light times the transmit pulse length over 2, which is the range resolution we defined earlier. However, because the range extent is the speed of light times the transmit pulse length, there is partial overlap in the scattering volumes between the 2 neighboring range gates. In addition to this, there is overlap in the scattering time between the 2 neighboring ranges. The mean scattering time for the range gate n+1 is shifted by pulse length over 2. Let us now investigate the effects of different receiver filter length t sub s and transmit pulse length t sub p. A simple model for a receiver filter is shown in the integral. A discrete time complex voltage signal, sample n, is obtained by integrating the continuous time complex voltage signal. In this first example, I have replicated the earlier case where the transmit pulse length and the receiver filter length were equal. If we have a situation where the receiver filter length is longer than the transmit pulse, the range extent of the radar echo is no longer defined only by the transmit pulse length. The effect of the receiver filter is to extend the scattering volume and range. In the limit where the transmit pulse length approaches 0, the range extent of the radar echo approaches c times filter length over 2. Conversely, if we have a transmit pulse that is longer than the receiver filter length, the region of range time probed by the radar is different. Again, the range extent of the receiver signal is defined by both the transmit pulse length and the receiver filter length. The minimum range extent obtainable in this case is defined by the length of the transmit pulse. When the receiver filter length t sub s approaches 0, the range extent of the received radar echo approaches c times pulse length over 2. For the remainder of this lecture, I will assume that the transmit pulse length and the receiver filter length are equal. We have now shown that the effective range resolution is speed of light times the pulse length over 2. Let us now determine how this is related to the bandwidth of the transmitted and received radio signal. A transmit pulse of length t sub p is defined in equation 2, using epsilon. I have used the Heaviside function u of t to define this pulse as a rectangular function. We can relatively easily Fourier transform this pulse and obtain the sinc function shown in equation 4. If we plot this signal in frequency domain using frequency in hertz on the x-axis and the spectral power on the y-axis, we can see that the half power bandwidth of the transmit pulse is approximately 1 over pulse length in units of hertz. Using the equation for range extent, delta r equals speed of light times the transmit pulse length over 2, we can relate the range resolution and bandwidth using the following relation, where the range resolution is the speed of light divided by twice the bandwidth. For example, if we had a bandwidth of 1 MHz, this would result in a 150 meter range resolution. In this case, the pulse length would be 1 microsecond. I have chosen to describe the range time behavior of signals using a discretized representation, as we use discretized signals in practice for radar signal processing. While there are some advantages to using a continuous representation, I believe that the use of discrete time signals will result in a more streamlined mathematical presentation. In order to derive signal processing techniques in discrete time, we will need a discretized range time diagram and a discrete time representation for radar signals. The following definitions are used for the discrete range time representation for radar signals. Capital T and capital R denote continuous time and continuous range. A discrete range, lowercase r, is a sample index that denotes range. It can be related to continuous range using the following relation. Lowercase r can also be associated with time. This means that the discretized range index corresponds to a round-trip propagation time of the radar pulse. A discrete time sample index, lowercase t, can be related to continuous time using the following relation. Both lowercase r and lowercase t have the same sample length, t sub p. We can therefore use both interchangeably to denote range or time. I will denote the continuous time complex voltage radar echo originating from a scattering volume using V sub r of capital T. The scattering volume corresponding to this signal is defined by the range extent of the range gate corresponding to range index lowercase r. Finally, I will denote the discretized scattered voltage originating from an area in range time space using V sub t, r. The discretized scattered complex voltage is related to the continuous time scattered voltage in the following way. In this case, I have made a range-dependent time shift when discretizing the scattered complex voltage. This allows us to simplify the equations that we will be using later on. This time shift corresponds to a one-way light travel time from the range of the scattering volume to the receiver. A different range-dependent time shift is therefore applied for each range. When discretizing the continuous time scattered complex voltage, I am assuming that no aliasing occurs. Here is a discretized range time diagram. In this diagram, epsilon of t is a discrete time signal that denotes the waveform that the radar sends out. This is a complex baseband signal. The length of a sample of this signal is denoted with t sub p. The box where V sub t, r is denotes the region of range time where the scattering signal originates from. Both r and t are integers. The signal m sub t denotes the received signal at time t. The received signal is also a complex baseband signal. Using our diagram, we can now relate the signal received at time t to the scattering from a volume of plasma denoted by V sub tr. The measured signal at time t is the range-delayed transmit signal multiplied with the range-time-dependent scattering from range r and time t. The reason for why the received signal immediately returns to the receiver in this diagram is because we are using round-trip time. In other words, we are taking into account the propagation delay between the transmitter and the receiver. This means that a line of constant time is slanted as follows. Both t and r in this case are in the same units, signal samples. For example, epsilon t minus r carries the following meaning. The transmit pulse sends out r samples before sample t. If we add radar scatter from another volume in range time space, we can now use the diagram to relate two samples of the transmitted signal to the received signal at time t. If we add a few more scattering volumes to our range time diagram, we arrive in the following situation. We can now relate 3 samples of the transmitted signal to 2 samples of the received signal. If we keep adding more scattering volumes into our diagram, we arrive at the following general formula that relates the received signal to the scattering volume in space and the transmitted signal. This is almost, but not quite, a convolution equation. The reason why this is not the usual convolution equation is due to the time dependence of the scattered complex voltage from volume R. The transmitted signal epsilon sub t can be thought of as a continuous train of transmit pulses, each defined by a phase and an amplitude. When there is no transmission, epsilon sub t is 0. Okay, now let's introduce 2 categories of radar targets: coherent and incoherent. This naming convention is not very useful because it does not really tell you what is going on, but this naming convention is commonly used. Coherent and incoherent scattering processes are simply categorized based on their spectral width. Radar scattering with a narrow Doppler spectral width decorrelates very slowly. So slowly that you can assume the scattered signal to be constant while the train of transmit pulses travels through the whole scattering volume. Incoherent radar targets, on the other hand, have a wider spectrum. Typically, one calls a radar scattering process incoherent if the complex voltage changes significantly over the time during which the train of pulses travels through the volume that it is probing. Incoherent scatter radar measurements of ionospheric plasma usually fall in this category. Some selected radar signal processing techniques that can be used for coherent targets are shown on the right. The matched filter, the inverse filter, linear algebra-based deconvolution, and pulse-to-pulse Doppler estimation. Coherent radar signal processing techniques can be used to estimate the complex voltage of the scattering process directly, and they operate on the amplitude of the received signal. Some selected techniques that can be used for radar signal processing of incoherent targets are shown on the right as well. These are the double pulse, the long pulse, multi-pulse, coded long pulse, lag profile inversion, and full profile inversion. The one thing in common for these techniques is that they estimate the second-order statistical properties of the radar echo and operate on lag products of the received signal. Let us begin by introducing techniques that can be used for coherent radar targets. For coherent targets, the complex amplitude of the scattered signal changes so slowly that we can assume it to be constant in time. In this case, the general radar measurement equation that we introduced earlier reduces to a convolution equation, as shown in equation 8. I have added receiver noise to this measurement equation as well. This is denoted by xi sub t. Xi is a complex normal random variable with a variance of 1 over signal-to-noise ratio. The most simplistic type of a radar is a radar that emits a short pulse. In this case, there is only one non-zero value for the transmit signal, epsilon t. In this case, we can model the radar transmit waveform using a Kronecker delta function. The delta function evaluates to 1 when the argument is 0, and 0 for all other values of the argument. The radar pulse can still have an amplitude and phase, which is denoted with epsilon naught. If we insert this definition to the coherent target radar equation we just defined, we obtain the following result. The received radar signal m sub t can be directly mapped to radar scattering originating from each range. We merely need to divide m by epsilon naught to obtain an estimate of the scattered complex voltage V sub r. The estimator for scattered complex voltage is shown in equation 12. In this case, the estimation variance is 1 over signal-to-noise ratio divided by the magnitude squared of the transmit pulse. In this case, the magnitude squared of epsilon naught corresponds to radar transmit power. This means that the more power we transmit, the smaller our estimation errors are. Let us now study the more general case for a coherent radar target, which is defined by the convolution equation shown in equation 13. The convolution equation is a linear equation which can be expressed in matrix form. The matrix A contains range-delayed elements of the transmitted signal. The matrix is diagonally symmetric. This type of a matrix is called a tuplets matrix. Or in some cases, a circulant matrix. This type of a matrix has the useful property that it can be diagonalized with the help of a Fourier transform. The vector M contains samples of the signal received by the radar receiver. The vector X contains scattered complex voltage for all the ranges that we are interested in estimating. And the vector Xi contains elements of the receiver noise. Using the matrix notation, we can obtain a maximum likelihood estimate of the scattered complex voltage as a function of range using equation 11. This equation is widely encountered in statistics. Sometimes this type of estimation is also called linear regression. The matrix formula for maximum likelihood assumes that the measured noise at different times are uncorrelated and identically distributed. Because we are dealing with a complex valued measurement equation, we need to remember the conjugate and transpose matrix A in this equation. In order for us to be able to use this formula, A conjugate transpose A has to be invertible. In other words, it cannot be singular. Matrix A contains the transmitted radar signal. Therefore, this is a requirement that needs to be satisfied by the transmitted radar signal. The covariance matrix of estimation errors for scattered voltage as a function of range are given by equation 12. For good radar transmit waveforms, A transpose conjugate A is close to a diagonal matrix. The constant P corresponds to the total power of the transmitted radar signal. In other words, how much power we transmit with our radar. In this case, the errors for the estimates of scattered complex voltage are uncorrelated in range. The error variance of the estimates of complex voltage are inversely proportional to the amount of transmitted power. Numerically, the most expensive part of equation 11 is inverting A conjugate transpose A. In practice, if a radar transmit signal is repeated, it is possible to pre-calculate most of equation 11, and the deconvolution of complex scattered voltage reduces to a matrix vector product, which is relatively inexpensive to implement numerically. As shown in the previous slide, the estimation error variance for complex voltage is 1 over the signal-to-noise ratio divided by radar transmit power P. The variance is thus inversely proportional to the amount of total transmitted signal power. Assuming that the radar has a limited peak transmit power, a longer transmit signal can result in smaller errors than a short pulse. Assuming that the transmit signal has a constant amplitude, which is usually the case, a radar transmit signal of length L non-zero samples will result in a factor of L reduction in estimation error variance compared with the short pulse of length 1 we just studied earlier. The concept of using long transmit signals to reduce estimation errors is called pulse compression, as we are effectively compressing more radar transmit power into the transmit signal to improve our estimate of the scattered complex voltage. This is the primary reason why longer coded transmit pulses are used for measuring coherent radar targets. As I stated earlier, a tuplets matrix can be diagonalized using a Fourier transform. What this means is that we can convert the convolution equation in time domain to a multiplication in frequency domain. This is a well-known property of the convolution operator and widely used in signal processing. The convolution equation describing the relationship between scattered complex voltage and transmit waveform can therefore be expressed using discrete time Fourier transforms in the form given in equation 15. If we now divide by the Fourier transform of the transmitted signal epsilon, we can directly obtain an estimate for the Fourier transform of the scattered complex voltage V of omega, as shown in equation 16. In order for us to be able to perform this operation, we cannot have zeros in the discrete time Fourier transform of the transmitted signal. For good radar transmit codes, this is the case. The last term in equation 16 is receiver noise. We can see what effect dividing by the transmit waveform has in the frequency domain. Each spectral component of the received signal is divided by the corresponding spectral component of the transmitted signal. Assuming that each spectral component of the transmitted radar signal has an amplitude larger than unity, the amplitude of the spectral components of the receiver noise are reduced. Finally, we can obtain an estimate of scattered complex voltage as a function of range by taking an inverse discrete time Fourier transform of m omega divided by epsilon omega. In typical situations, it can be shown that equation 16 is equivalent to the matrix maximum likelihood estimate shown earlier. The frequency domain technique has the advantage that we can implement it with the help of a fast Fourier transform, which is numerically more efficient than the matrix formula shown earlier. We can also express the division in frequency domain as a time domain filter, as shown in equation 17. This filter is often called the inverse filter. If we convolve the complex voltage received by a radar receiver with the inverse filter, we obtain an unbiased estimate of the scattered signal as a function of range. Again, this can be shown to be equivalent to the matrix maximum likelihood estimate shown earlier. The match filter is a commonly used technique in radar signal processing for deconvolving a radar transmit pulse. Unlike the previous estimators I described earlier, the match filter is a biased estimator. When applying a match filter, the estimated complex voltage of the scattered signal has estimation artifacts, which are often called range side lobes. In matrix form, the match filter is defined by equation 24. We can compare this to the maximum likelihood estimator shown earlier. The main difference is that this estimator is missing the A conjugate transpose A inverted part, which would be needed in order to make this estimator unbiased. However, for good radar transmit codes, A conjugate transpose A is close to a scaled identity matrix, in which case both the maximum likelihood and the match filter produce a similar estimate. In time domain, the match filter can be expressed as a convolution of a conjugated and time-reversed copy of the transmitted signal with the signal received by the radar receiver. Equations 25 and 24 are equivalent. Unlike the estimator variance for the inverse filter, the estimation variance for the match filter does not depend on the transmit signal. It only depends on the total power of the transmitted signal. However, the estimation variance of the match filter in the case of good radar transmit codes does not often significantly differ from the estimation variance for the inverse filter. As I will demonstrate later, the estimation bias for a match filter can sometimes be problematic. I will now show a simple example of deconvolving a coherent radar target. I will use a point radar target, where only one range has a non-zero amplitude radar echo. We can express the scattered complex voltage V sub r, in this case using equation 27. Using the radar equation for a coherent target, the radar echo in this case is a delayed copy of the transmit signal, as shown below. In this case, I have used the 13-bit Barker code as the radar transmit signal. This is an often used radar transmit signal which has many beneficial properties. If we now apply the formula for the match filter estimator, we can see that the estimator is a time-shifted autocorrelation function of the transmitted signal centered on range R0, the location of the true radar echo. The plot shows the output of the match filter estimator. The estimator correctly produces an estimate of the scattered complex voltage at range R0. However, around this range, there are estimation artifacts. These are referred to as range side lobes. These side lobes arise due to the autocorrelation properties of the transmitted signal epsilon. Here is the same example, but now evaluated with Python and with simulated receiver noise. On the top left, you can see the true scattered complex voltage as a function of range. The plot on the top right shows the simulated radar measurement, including both the radar echo and the receiver noise. The lower left plot shows the transmit signal, which in this case is the 13-bit Barker code. The middle plot shows the inverse filter. This filter can be used to produce an unbiased maximum likelihood estimate of the scattered complex voltage. The plot on the lower right shows the match filter. The two plots shown compare the inverse filter and the match filter estimators for scattered complex voltage. The inverse filter is shown on the left and the match filter on the right. It is clear that the match filter estimator has estimation bias or range side lobes, which the inverse filter does not. Both estimators have a very similar estimation error, as the noise in the estimates is of comparable magnitude. It is clear that the inverse filter estimator is a better estimator in this case. You can download the code I wrote for this example on GitHub. This animation shows the process of convolving a radar echo using an inverse filter. The inverse filter is shown above. The middle plot shows the simulated radar echo. Because we have radar scattering only from one range, the radar echo is a delayed version of the transmitted signal, epsilon of t. This is therefore what the 13-bit Barker code looks like. The bottom plot shows the output of the received radar echo convolved with the inverse filter. The output of this convolution operation is an unbiased estimator of the true scattering of our simulated radar target, which only has scattering from one range. This animation demonstrates the use of a match filter. In this case, the match filter is a conjugated version of the transmit signal itself. The match filter is shown above. The 13-bit Barker code is a fairly good transmit code. However, our estimate of scattered voltage as a function of range has bias, as you can see below. This bias is due to the autocorrelation function of the transmit code having non-zero values at non-zero lags of the autocorrelation function. These estimation artifacts are called range side lobes. They can typically appear around a strong point-like radar target when using a match filter. Good radar transmit signals or radar transmit codes for measuring coherent targets exist. They can also be searched for using optimization algorithms. In some cases, even perfect radar transmit codes can be created mathematically. The main optimality criteria for radar transmit codes in the case of coherent radar targets are shown in equations 22 and 23. The criterion shown in equation 22 means that the code should be such that the non-diagonal elements of the matrix A conjugate transpose A should be as small as possible in magnitude. This means that the values of the autocorrelation function of the radar transmit code at non-zero lags should be as small as possible in magnitude. This criterion minimizes the magnitude of the range side lobes when using a match filter. The criterion shown in equation 23 states that the estimation error variance should be as small as possible. This criterion, in my opinion, is better. Examples of good radar transmit codes for coherent targets are Barker codes, perfect codes, and chirps. Barker codes. These are codes that have autocorrelation function side lobes with a magnitude of 1 or 0. Perfect codes. These codes have no autocorrelation function side lobes. Such codes also result in a minimum theoretical estimation variance. So in terms of both criteria, these codes are optimal. However, perfect codes require use of amplitude modulation. One example of a mathematical method for creating a perfect code is as follows. You can take any signal, epsilon sub t, and Fourier transform it. You then divide the Fourier transform of the signal by the magnitude of the Fourier transform. Finally, you inverse Fourier transform this expression to obtain a perfect code. Finally, chirps. These radar transmit waveforms that consist of frequency sweeps. Such radar transmit waveforms are commonly used in radars. Here is a table of all known binary phase Barker codes. The longest sequence known to exist has a length of 13 bits. In this table, the pluses and minuses are the values of the signal samples. For example, plus plus minus would be 1 1 minus 1, as shown in this little plot that I've sketched. While there are no binary phase Barker codes longer than 13 samples, there are longer polyphase codes, which have the property of Barker codes that the autocorrelation function side lobes are less than or equal to 1 in magnitude. As far as I know, polyphase Barker codes have not been used for incoherent scatter radar, primarily because signal generators used with existing radars do not support them. However, they would be very useful for many applications, and they will probably be used in the future. Here's an example of an amplitude-tapered chirp transmit waveform, which consists of a frequency sweep. The autocorrelation function of this signal is peaked around 0 and has very low values elsewhere. This type of a transmit waveform is a very good radar transmit signal for coherent targets. One example of chirp waveforms that has been in use for a very long time is this. Bats emit ultrasonic sounds, which are essentially frequency chirps, and they use these auditory signals to detect obstacles and insects at night. While this is not per se a radar, the same principles of radar can also be applied to sound. Remote sensing using acoustic waves is called sonar. One can only presume that some part of a bat's brain is conducting an operation similar to the match filter that we described earlier, to estimate the distance between itself and various acoustic scattering objects in its surroundings. By using a long acoustic chirp waveform instead of a short pulse, bats can compress more power into the emitted acoustic signal and thus improve the fidelity of the sonar measurement. Coherent radar targets still have a finite spectral width. This means that while the scattered radar echo can be assumed not to change significantly over the duration of one radar transmit waveform, from pulse to pulse the scattered voltage can change. By sending out radar pulses and estimating the complex amplitude of the scattered signal for each pulse, we can sample the radar scattering as a function of time from pulse to pulse. The length of the time interval between pulses, in this case, is called the interpulse period, which is often denoted with the acronym IPP. The temporal spacing of pulses is denoted with T sub IPP. In this scheme, each radar pulse can optionally be coded using a transmit signal, which can be deconvolved using techniques that we described earlier. Coding is often used to reduce the estimation error variance of the scattered complex voltage. By sending out pulses at regular intervals, we can sample the scattered signal with a time resolution of TIPP seconds. This corresponds to a maximum Doppler bandwidth of 1 over TIPP. This is the maximum bandwidth that the scattered signal can have before it Doppler aliases. We can now use the pulse-to-pulse measurement of scattered complex voltage as a function of range and time to estimate the power spectrum of radar echoes as a function of range and Doppler shift. In order to be able to do this, the power spectrum of the radar scatter needs to be sufficiently narrow so that spectral aliasing is avoided. The Doppler spectrum for each range can now be obtained by averaging the magnitude squared of the discrete time Fourier transforms of the scattered complex voltage measured from pulse to pulse for a certain range. The mesosphere is pretty much the only part of the ionosphere which is a coherent radar target for incoherent scatter radars. This region of the ionosphere is weakly ionized and highly collisional. Due to the collisionality of the plasma, the spectral width of the incoherent scatter spectrum is very narrow. This allows us to treat the ionospheric scatter from the D region as a coherent target and to use the pulse-to-pulse technique for spectral estimation. Here is an example measurement of the D region of the ionosphere made using the Hicamarca incoherent scatter radar in Peru. The figure shows estimates of the power spectrum of the radar scatter between 90 and 120 kilometers. Above approximately 100 kilometers, the spectral width is so large that the received radar signal is Doppler aliased. Planetary objects often have a very narrow Doppler extent. This allows us to use coherent radar target techniques when estimating the radar scatter from planetary surfaces. Planetary targets are also very far away. Often very long transmit pulses are needed in order to reduce the estimation variance of the scattered complex voltage. The image shown here is a measurement of the Range-Doppler spectrum of the Moon. The brightness denotes the amount of scattered power as a function of range and Doppler shift. In this image, the horizontal axis denotes Doppler shift and the vertical axis denotes range. Due to the range and Doppler variation of different points on the Moon, a pulse-to-pulse Range-Doppler spectrum measurement can be used to map radar scatter power originating from different regions on the Moon. We're now done with discussing coherent radar targets. Let's move on to incoherent targets. Let us revisit the range time diagram that we used previously to describe how we perform pulse-to-pulse measurements of the scattered signal Range-Doppler spectrum. Recall that the Doppler bandwidth of this type of a measurement is 1 over the interpulse period. The interpulse period is the spacing between transmit pulses that I use to measure the value of the scattered complex voltage as a function of range. In the case of radar measurements, there is another aliasing that occurs. It is range aliasing. Range aliasing occurs when the round-trip propagation delay for the radar echo at the furthest distance is longer than the interpulse period. The longest range that we can measure without range aliasing is thus determined by the interpulse period as well, and it is defined as the speed of light times the interpulse period over 2. We will denote this with R alias. For example, consider a radar target at this range. A radar echo from this range, corresponding to the first radar transmit pulse, will arrive simultaneously with the radar echo from the lower range, corresponding to the next radar pulse that was sent out. If we use the same radar transmit signal for each pulse, we have no way of determining the true range of the radar echo in this case. It could be either R0 or R1. If we combine the expression for range aliasing and Doppler bandwidth, we can see that these two are inversely proportional to one another. If we increase the maximum range that we can observe without range aliasing by increasing the interpulse period, we reduce the Doppler bandwidth that we can observe without Doppler aliasing. This is called the Range-Doppler dilemma. An incoherent scatter radar measurement of the ionospheric plasma is a prime example of a case where the coherent target pulse-to-pulse Doppler spectrum estimation technique cannot be used. The range extent of the ionosphere is over 1,500 kilometers. This implies that an interpulse period longer than 10 milliseconds needs to be used in order to avoid range aliasing. However, the incoherent scatter spectrum is about 20 kHz wide in the F region, in the case of a 500 MHz radar. This implies that we would need to use an interpulse period less than 50 microseconds long in order to avoid Doppler aliasing. These two requirements cannot be simultaneously met. In this case, the target is called Range-Doppler overspread. This, however, does not mean that we cannot measure the Range-Doppler spectrum. We just cannot use techniques that we typically use for coherent targets. The easiest technique to understand for measuring Range-Doppler overspread incoherent radar targets is the double pulse method. With this method, two radar pulses are sent by the radar transmitter. The separation of these two radar pulses is tau. The received echoes for these two radar pulses can be used to estimate the lag tau of the autocorrelation function of the scattered complex voltage. The estimator is shown in equation 31. If we want to estimate the autocorrelation function for range R, we use the received signal m at time r and r plus tau. The received signal at time r is divided by the complex amplitude of the transmitted signal at time 0. And the received signal at time r plus tau is divided by the transmitted signal at time tau. This has the effect of undoing the transmit signal at range R. We then multiply these two received complex voltages with one another to form an estimate of the autocorrelation function at range R and lag tau. If we expand the product of the two received voltages, we get a lot of terms, 9 terms in total. If we then look at the expected value of our estimator, we can see that there is only one term that is non-zero mean, and it is the first term. The other terms are zero mean due to several reasons. First of all, scattered signals from unmatched ranges do not correlate. Also, receiver noise does not correlate with the scattered signal. And finally, the receiver noise does not correlate at different times. This estimator is therefore an unbiased estimator of the autocorrelation function of the scattered complex voltage from range R and lag tau. Perhaps the most common technique in use nowadays for estimating the autocorrelation function of scattered complex voltage as a function of range and lag is the coded long pulse technique. This can also be seen as a generalization of the double pulse technique. However, in this case we cannot rely only on the fact that the echoes from different ranges are uncorrelated. we must rely on the properties of the radar transmit code to ensure that our estimate of the autocorrelation function is unbiased. In the case of the coded long pulse technique, we send out a group of radar transmit pulses. In the case of this example, there will be a group of 8 radar transmit codes. Each radar pulse consists of a transmit signal of some length. In the case of this example, the length of the code is 4. Each pulse has a phase and amplitude denoted with epsilon t. In this case, we will assume that epsilon t is either 1 or minus 1. From this it follows that if we multiply epsilon t with the conjugate of epsilon t, it will always be 1. If we want to estimate the autocorrelation function of the scattered voltage at range r and lag 1, we can use 3 different pairs of the received complex voltage, as they will all contain information about lag 1 of the scattered complex voltage at range r. I will only use the first pair to demonstrate the technique. Consider the following estimator for autocorrelation function. In this case, we average over all of the codes in the code group, and we multiply received signal at time r with received signal at time r plus 1, conjugated. We also use these terms here to undo the coding, just like we did with the double pulse. If we expand this expression, we can arrive at this expression. Here, the coding has been undone for range r. All of the other terms that include scattering from different ranges, they still have code terms attached to them. If we now look at the expected value of our estimator for the autocorrelation function at range r and lag 1, we arrive at this. I have already dropped all of the cross terms where the scattered voltage is at a larger range offset than 1, because in this case the scattered voltage is uncorrelated, because there is no overlap in range. However, all of these terms are correlated. This term, for example, is correlated because it comes from the same range. This term also comes from the same range, so it's correlated. These terms come from a partially overlapping range, because if you have 2 neighboring range gates, in the range time diagram, there's partial overlap. So if this would be, for example, r, and this is r plus 1, these 2 scattered complex voltages will be correlated. Okay, so the term that we want is the first term, because it tells us about the autocorrelation function at range r. We want to get rid of all of these other terms. We want to figure out how to get rid of all of these terms. Okay, and in order to do that, we need to rely on the transmit code. We need to rely on these values here. And that's why we need a group of codes. One code is not enough. One double pulse is not enough. We need to average over a sum of multiple codes. And we essentially do this. We find a group of codes which has all of these properties. We want all of these terms to become 0 after we have averaged over a group. Okay, there's one trivial way of doing this. If we have infinitely many codes and they're pseudorandom codes, they will have this property. However, there's also a clever technique called the alternating code technique, which is used at ISCAT. In this case, analytically, after going over the group of codes, in this case 8 different codes, these terms average out to 0. And that's how we get rid of all of these terms here. That's how we get rid of all of these terms. After summing over the codes in a group, we are only left with this first term. And here's the group of codes that does it. This is the so-called 4-bit strong alternating code set. So there are 8 different transmit pulses with these amplitudes. After sending out all of these 8 codes, we will have an unbiased estimator of the autocorrelation function at range r and lag tau. Here's an example of a longer alternating code. In this case, the horizontal axis is the code index, and this axis is time. In this case, black means that the code element is 1, and white means that the code element is -1. I'd like to briefly finish off with a new technique which is pretty neat, because it allows us to convert an incoherent radar target into a form where we can treat it as a convolution equation. Now, a convolution equation is the equation that we obtain when we were dealing with coherent targets. The technique I'm going to outline is called lag profile inversion. To apply lag profile inversion, we still need a group of codes, but this group of codes does not have to have perfect cancellation properties that we discussed earlier when discussing the coded long pulse technique. The lag profile inversion method is a relatively flexible technique for estimating the autocorrelation functions of an incoherent scatter radar target as a function of range, and it is relatively easy to understand. We start with the general radar equation for a radar target, which allows the scattered complex voltage to change as a function of time and range. This is not the convolution equation because of the time independence of the scattered complex voltage. What we do next is we multiply the signal received by the radar with the conjugated and lagged version of itself. We then make the assumption that scatter only from the same ranges correlates. Ignoring partial overlap for neighboring ranges to arrive at equation 46. In this process, we move all of the zero mean random variable terms that arise from the product of two sums in equation 45 to a zero mean random variable, xi prime. We use the fact that if we multiply two random variables, the product is related to the expected value of the product of these two random variables, plus a zero mean random variable. If we now take equation 46 and use a little bit of shorthand, we get equation 47. This is now a convolution equation which relates the lag product of the measured signal with the autocorrelation function of the radar echo as a function of range. We get one convolution equation for each lag that we want to estimate. The convolution kernel is a lag product of the transmitted radar signal. We can solve this convolution equation using any of the methods that I described for coherent targets, but perhaps the most flexible technique to use is the matrix deconvolution method. This technique is described in much more detail in the following paper by a colleague of mine, Ilkka Virtanen. That's all for now. If you have any questions, I'll be happy to answer them when I come back from skiing.